So, the next very important module that we are going to talk about is implementing, first conceptualizing and then implementing what are called perfectly matched layers. So, to motivate this, first we will start with why do absorbing boundary conditions fail, and then the remedy. Okay. So, you have some motivation and then we come to perfectly matched layers. One thing I want to mention, this perfectly matched layers, it's a recent sort of formulation, 1990s is when it was formulated. It's not restricted to FDTD. Even FEM you can implement PML and people have done so. Okay. So, what I am telling you will start with the theoretical development, then implementation in FDTD, but you could also implement in FEM. Okay. Right. So, the failure of absorbing boundary conditions is what we start with, right. So, let us jump in to this discussion by starting by considering a lossy medium. Okay. So, what is different is it is a lossy medium. Previously, when we had looked at absorbing boundary condition, what did we start with? 1D vacuum. In 1D vacuum, we imposed the boundary condition and we found that absorbing boundary condition was perfect, right? There was no reflection whatsoever. So, we will keep the discussion limited to 1D, but now change it to a lossy medium. That is the only difference. And here we will find that the ABC is not able to deal with it. Okay, so, let us see how. So, a lossy medium is characterized by a conductivity which is non-zero, right. And for now we will just, to keep things really simple, we will not even consider a dispersive medium, we will just consider a simple whatever we were doing, d is equal to epsilon E, okay. So, single frequency kind of a thing. So, this is your Maxwell's equation everyone is familiar with, curl of H is J plus dt by dt, right. So, this should be there should be a T also over here, but never mind, similarly everywhere, okay. So, it is understood. I replace the current term by Ohm's law, okay, and I replace d by dt by j omega, okay, standard, right. So, all of these equations should have a T dependence, okay, and then we are doing the e to the j omega t approximation, right. So, that gives us this, which all of us have seen during undergraduate courses. And then the standard procedure from here is to try to extract a effective permittivity. So, what do? I pull out a j omega epsilon naught, okay, and whatever is left inside over here is in this bracket, okay. So, what does this term look like? It looks like a effective relative permittivity. So, I will call that epsilon r prime, okay, which is obviously complex. So, this is just like our original Maxwell's equation where supposing I put sigma equal to 0, I get epsilon is epsilon naught times epsilon r relative permittivity, okay, fine. Then what do? So, 1D medium, so very simply I will take the two Maxwell's equations, take curl of the other and get a wave equation. And this wave equation that I get is of this kind over here. The only change that happens is that instead of k naught squared, I get a epsilon r prime, whatever was the relative permittivity over there comes in over here, okay. So, I am going to call this term over here as k prime square, okay. We have derived wave equation many times, so we will not derive it once again over here. We are considering a homogeneous lossy medium. So, you can imagine like I have say water and I am doing FDTD within that and just a 1D medium, we are not even considering object right now. So, we want to see what is the impact of the ABC in a lossy medium. We saw that in a loss free medium, ABC was perfect, there was no problem with ABC, okay. When I solve this wave equation, this is the solution that I get as before, right, no surprises over here. What is this? This k prime squared I have already mentioned over here, k prime squared is equal to k naught squared epsilon r prime, right. And so, from here I can get k prime as just square root of this expression. Square root of a complex number is going to give me a complex number. Okay. So, I am going to write this as k some real part minus j times k some imaginary part. Okay. So, the solutions I mentioned are both plus and minus, right. So, this is going to give me a forward and a backward wave, right. So, what does the forward wave look like? Same thing, right. So, I am going to get e to the j omega t minus k prime x. Now, let us expand that in terms of real and imaginary parts. So, I am going to get e to the j omega t minus k r x, and then what happens next? Minus into, yeah. So, what is that going to be? Should be plus or minus. So, minus j into j is going to give me a plus 1, right. So, let us just check this once again if this is what we would get. Yeah. So, what I will do is I am going to write this as plus. Okay. It is up to me how to write it, right, plus or minus, the sign will get absorbed into ki. Okay. So, if I write it like this, what happens to this sign over here? Minus kix. Okay. Why would I do that? Right, as the wave is traveling through a lossy medium, it should decay, it should not gain in amplitude, right. Okay. It was correct, right? Because no, how j, oh, there is a minus also with the sign of x, right. So, that became plus and a minus sign. Yeah, okay, fine. Right. So, too many minus signs. So, decays as wave travels. Okay. And the backward wave plus k prime x okay. Does this wave decay? It had better decay. It is decaying, right? Which direction is this wave traveling? It is traveling in the minus x direction. So, x is decreasing over here, right. So, this wave will also decay as it travels. So, it is correct. Always check that you are getting a physically meaningful solution over here. One quick thing I want to point out, that this k prime, which I have written as kr minus jki, both kr and ki will turn out to be positive numbers. Okay. If I had the opposite sign convention for time, if I had e to the minus j omega t, what will happen? You will get a plus sign over here, because your time convention does not change the physics of the problem, but the wave will decay. Okay. So, some places, as I mentioned before, will have a e to the minus j omega t convention. In that case, the effective permittivity will have a positive imaginary part. Okay. Okay. So, now what do? We have, I mean, the situation we are considering is this is my boundary, and I have a wave that is incident over here, and we are asking that is there a reflection? Okay. When the medium was lossless, we saw that r was equal to 0. We already seen that, but now what happens? Okay. So, what do I have as the total field over here? So, let us come over here. So, this is my background, this is my, so the total field is going to be incident plus reflected, right. We are not so far going into FDTD implementation, just total field is incident plus reflected, okay. And what was my the boundary condition that I was going to employ? Are d by dx, was it plus or minus for the right hand boundary? Plus 1 by c d by dt E is equal to 0. That is what we are imposing, okay. So, right. So, these are the incident is a forward travelling wave, reflected is a backward travelling wave, okay. So, I am going to write this as, so e to the j omega t minus kr x minus kix, and what do I write the backward wave as? R, reflection coefficient, e to the j omega t plus kr x plus kix, okay. Now, I am going to put these two together and impose this boundary condition, okay. So, the first, so the derivatives now will happen with respect to space, first one d by dx. So, what is the first term that I get? I get a minus j k r, right. Then I get a minus k I, this is d by dx put on incident field, plus r times, now what will I get? J k r plus k I, this takes care of the d by dx part. Then comes 1 by c, what is the time part over here? J omega plus r j omega equal to 0. That is my, this is imposing ABC on, just imposing ABC, okay. So, from this all what we can do is gather all the r's on one side and write an expression. So, what I get is, so kr minus omega by c this is the reflection coefficient. So, what does that tell you? In our ABC, what is the one knob we have in our hand to impose the boundary condition? Like in the 1D ABC or 2D ABC, we were putting a cos theta factor over the 1 by c. So, in some sense you can play around with that number c, right, you can multiply it by some cos theta or whatever. But now when you look at this expression, what happens over here? First of all, look at when ki is 0, right. So, lossless what happens now? Can I make r equal to 0? Yes, how? Right. So, if I put c is equal to omega by kr, I am done, I get 0 reflection coefficient. But if I have lossy, that is ki not equal to 0, there is no hope, I cannot make this expression 0. How will I make this expression 0? There is always an imaginary part. I can make the real part 0, but the reflection coefficient will always be there. If no, omega by c is a real number. How can omega by c equal to kr minus jki? Yeah, so how can a real number be equal to complex number? Can't be, right? So, there is no value of c that I can play around with that can make this expression go to 0. So, r equal to 0 not possible. Okay. So, the conclusion is that even in a 1D, the ABCs fail if the medium is lossy. Okay. So, what is a practical way around this situation? Supposing you had to live with it, you had a lossy medium and you wanted to impose ABC, what was the way around it? So, notice what are these waves? What kind of waves do we call these with a decaying part? Yeah, correct, say that again. Evanescent waves, right? So, these are evanescent waves, right? So, what is the one property of evanescent waves that you can utilize even though the boundary condition is not perfect? They decay with space, right? So, you would have to put the absorbing boundary condition further away from the objects, so that even though it is imperfect, the wave will hit it, but still it will decay. Okay. So, the workaround is larger distance between the object and boundary, right. As it is, if the moment I deviate from 1D, anyway I am going to have a loss, I mean a reflection coefficient, non-zero reflection, that we have seen before, right. So, to summarize, there are two reasons that we say that the ABCs fail. The first is of course that non-normal incidence gives a reflection coefficient that is non-zero. We already saw that, and the second is lossy mediums. Okay. So, this motivates us to go for something else. We want to see if there is another solution that does not increase the size of my computational domain a lot and gives me a good accuracy. Okay. So, this part is clear.